We continue with some problem solving and exponential modeling. In the previous video, we looked at the first part, that is uh, oil production starting from 1950 to 1972, and the rate at which the oil production was increasing was about 7%. And we calculated that in 1972, based on the growth rate of oil production of 7%, we have about 2.3 billion in oil production. So this was the number that we got, about 2.3 billion of oil production in 1972. So continuing from that, using the result in part A, which is 2.3 about 2.3 billion tons, and to be really specific, it's that much billion tons, 2.29495 billion tons in 1972. So the question says, what if the growth rate continued? What would be the oil production in 2008? So we're looking at oil production from 1972 to 2008 at the growth rate of 7%. So R is 0.07. It's a period of 36 years because 2008 minus 1972 is 36. So within these 36 years, if the growth rate was 0.07, which is 7%, the initial quantity that we started with, so this is the oil production in 1972, what is the final quantity in 2008, assuming a great growth rate of 7%? It would be, when we simplify everything, about 26.2 billion tons. Since our initial quantity is in billions of tons, it is the units would still be billion tons. So it's 26.2 billion tons in 2008. So the oil production, based on a 7% increase starting from 1972, when the initial oil production was about 2.29495 billion tons, would have to be 26.2 billion tons, which is much, much larger than what actually happened. This is the number that was given to us, 3.9 billion tons in 2008. That was given to us. So compared to 26.2 billion tons in 2008, assuming a growth rate of 7%, this number is way smaller, which means that between 1972 and 2008, the rate at which the oil production was increasing would have to be much less than 7%. So that's the conclusion we can make, because if it was 7%, it would be 26.2 billion, but what actually happened was way less than 26.2 billion, which means that the growth rate must have been way less than 7%. Now let's look at the next part. It says, using the result in part A again. So part A, our result was this: a growth rate of 7% starting from 1950. The oil production in 1972 would have been 2.29495 billion tons. Now, assuming a growth rate of 3% between the next time period, 1972 and 2008, a growth rate of 3% in a span of 36 years, we're trying to figure out the quantity Q, that is the amount of oil production in 2008. So instead of a 7% increase, we are now assuming a 3% increase. Let's see what we get as our oil production in 2008. It's 6.65 billion tons. If we compare it to what the real or the actual oil production was in 2008, it was 3.9 billion tons, which was which is really way less than 6.65 billion tons. So what can we say about the actual growth rate R between 1972 and 2008? From part B, we know it would have to be less than 7% because if it were 7%, the oil production would have been 26.2 billion when it actually was 3.9 billion, which is way less. So even assuming a 3% growth rate, we still have a quantity which is almost double 3.9, almost. That is 6.65 billion tons. So the actual growth rate is not only less than 7%, it would also have to be less than 3%. So when we do the calculations for a 7% growth rate in the time period 1970 to 2008, or a 3% growth rate between 1972 and 2008, it would still have to be um, less than 3% clearly. So the growth rate must have been way less than 3%. In parts C and D, we're asked to um, figure out the oil production in 2008 based on a 7% growth rate and a 3% growth rate. Now, when we did our calculations of oil production in 2008 based on a 7% growth rate, we got about 26 million tons and billion tons, which is way above what it really was. It was 3.9 billion tons. When we did a calculation with a 3% growth rate, we still got a number higher than what it was. We got 6.65 billion tons when the real value was 3.9 billion tons. So from this, it's clear that the growth rate is less than 7%, it's even less than 3%. So the initial quantity that is the initial oil production in 1972 was about 2.29495 billion tons. In 2008, the actual oil production was 3.9 billion tons in a span of 36 years, so that is time t. So plugging in all the numbers, it's clear that the only thing that's missing is R. Now try to plug in numbers for R in your calculator and try to get as close as possible to 3.9, which means in your calculator enter 2.29495 times 1 plus a number for R to the 36 and see which number R gets you closest to 3.9. So obviously the number would have to be less than 0.03 because for 0.03 we got a 6.65 billion tons of oil in 2008, but we know it's much less than that. So as you keep plugging in smaller and smaller numbers, you'll see that what works best is 0.015. So 0.03, which is 3%, is much larger than what it should have been. So we try to plug in smaller numbers, 0.01, 0.015, and so on, and see what works best. That's called the trial and error method. So once we do that, what worked best was, after I did the trial and error method, it was the number 0.015. 0.015 corresponds to, if I change it to a percent, 1.5%. So if the increase per year of oil production was 1.5%, then that works well because we know that the oil production in 2008 was 3.9 billion tons. So plugging in all the numbers, we get closest to 3.9 billion tons in 36 years when the rate R is 1.5%. Now, in the next example, we're going to see an important application of the exponential function that is using when it's applied to the half-life of carbon-14, which is a radioactive substance with a half-life of 5,700 years. So the half-life of carbon-14 is 5,700 years, which means if we start off with 1 gram of carbon-14, in 5,700 years, we'll have only half a gram of carbon-14. In another 5,700 years, we'll have only 1/4 gram, and then it keeps decreasing and halving every 5,700 years. Every time it's half of itself. So the equation that we set up, since we are given the half-life, it's Q equals Q naught half to the T over half-life. So that is Q equals Q naught half to the T, that is time at which you're calculating the quantity that remains, divided by half-life, which is 57 years. So this is the equation that we plugged the numbers into. So let's answer the question in part A. It says you find a piece of cloth painted with organic dyes. By analyzing the dye in the cloth, you find that only 63% of the carbon-14 originally in the dye remains. So the dye had a certain amount of carbon, but only 63% of it is left right now. So we want to know how much time has passed by, which means how long has it been since the dye was started off. That is, how many years have passed since or how old is the cloth is the question. So Q equals Q naught half to the T over 5,700, which is the half-life. Now, if Q naught was the original quantity of carbon, only 63% of it remains after a certain number of years that we're trying to figure out. Off translates to time, 63% is 0.63. So Q is equal to 0.63 times Q naught. So substituting Q equals 0.63 times Q naught is equal to Q naught half to the T over 5,700. Divide both sides by Q naught, and that conveniently cancels off. So we divide by Q naught and we divide by Q naught. The two cancel off. And we get 0.63 equals half to the T over 5,700. Now in this equation, the only unknown is T. And in order to solve for T, we need to use logarithmic functions. And if you want to avoid that, it can be done by trial and error method. Remember that if the unknown is an exponent, then the techniques that we use for linear equations, for solving linear equations like multiplying, dividing, subtracting, adding, none of these work. So the only way you can solve it is by trial and error method or by actually using the log function, which we're trying to avoid. So in your calculator, plug in values of t to see what best fits this particular equation. So we want our answer to be as close as possible to 0.63. So we plug in the numbers on the right along with t. So in 5,700 years, we know that carbon-14 is going to be half of itself. But at this stage, it is 0.63 of itself, which means that the time t would have to be less than 5,700 years, because if it is 5,700 years, you know it's going to be half of itself, which is 50% of itself. If it's greater than 5,700, then it would have to be less than 50% of itself. So thinking about that function, I started off with about 4,000 to just get a feel for what answers I get. I got about 0.61, which was pretty close to 0.63. So I just tried to close into that number by decreasing the number of years to 3900. It became closer. I decreased it a little further, and 3800 got me closest to 0.63. So what works best in that equation is about 3800 years. If you try to plug in numbers randomly, it's not going to work out. So just based on your knowledge of or definition of half-life, um, try to see what you can plug in. You shouldn't be plugging in too many numbers. You have to get a feel for it and then try to get closer and closer to the actual value. So it takes 3,800 years for carbon 14 to become 63% of itself. So the cloth would have been painted about 3,800 years ago. So this is how um, the half-life of carbon-14 can be used to determine the age of these old objects. Continuing with a similar example, again, it's the same carbon-14 with a half-life of 5,700 years, which means in 5,700 years it becomes 50% of itself. Double that and it becomes half of 50%, which is 12.5%. Triple that, so that's 17,100 years, it becomes 12.5%, and so on. So a well-preserved piece of wood at an archaeological site has 12.3% of carbon-14 that it must have had when it was alive. Estimate when the wood was cut. So this is an important number. Only 12.3% of the carbon-14 remains. So 12.3% of Q naught is equal to 1.123, I'm sorry, 0.123 of Q naught. That is equal to Q. Q is that much. How many years have gone by is the question. If the half-life is 5,700 years, we know this is going to be the equation. Q is 12.3% of Q naught, and that's written in decimals, is equal to Q naught half to the T over 5,700. Divide both sides by Q naught, and it cancels off. 0.123 is equal to half to the T over 5,700 when the Q naughts cancel off. Now, the only unknown is T, and we have to solve for T. And as I said before, the techniques of adding both sides or subtracting both sides, dividing or multiplying both sides with the exact same number doesn't work in these sort of exponential equations. That works only for linear equations. So we just try to figure out what T works best for that equation. So I know that the time would have to be less than, or sorry, more than 17,100 years, because it would have to be more than 17,100 years for it to decay less than 12.5% of itself. So I plug in the next number that I think should get me close to the final answer, and it does. 17,200 years when plugged in to this equation gives me 0.123 or close. So the wood is about that old, 17,200 years old. Now the final question, it says, is carbon-14 useful for establishing the age of the Earth? So the age of the Earth is about 4.5 billion years. The half-life of carbon-14 is about 5,700 years that we know from the question. Now remember that in a very short time, like in 17,100 years, if you remember what we did here, 17,100 years, the carbon is 12.5% of itself. So if it's 12.5% of itself in such a short time, which is 17,100 years, and then in the next, it becomes half of 12.5%, and it just keeps um, becoming half, so decaying, becoming half of itself every 5,700 years. Now, after 4.5 billion years, if the quantity of um, carbon 14 is half of itself every 5,700 years, then what is left of it after 4.5 billion years is close to zero. It's so close that it's almost impossible to detect it. So it is not possible to use carbon 14 to figure out the age of the Earth, because the age of the Earth is way